Mount Shasta rises above Northern California with a presence so commanding that it seems almost detached from the surrounding landscape. From more than 100 miles away on a clear day, its snow-covered summit dominates the horizon, appearing calm, timeless, and unchanging. Yet appearances have always been deceptive. For generations, travelers, geologists, climbers, and nearby communities have admired its beauty while quietly acknowledging another reality. This is not simply one of America's tallest mountains. It is one of the most closely watched volcanoes in the Cascade Range, because its remarkable past continues to shape expectations about its future. Its enormous size inspires confidence, almost giving the impression of permanence. In reality, Mount Shasta represents millions of years of repeated construction and destruction. Entire portions of the volcano have collapsed. Powerful eruptions have buried valleys beneath volcanic debris. Rivers have been redirected. Thick blankets of ash have spread across distant landscapes. Massive mudflows have traveled astonishing distances, transforming everything in their paths. Every layer visible along its slopes preserves evidence that the mountain has never remained the same for very long. Scientists understand that dormant volcanoes often create a dangerous illusion. Human lives unfold over decades, while volcanoes evolve over thousands of years. A mountain may appear completely inactive during several generations before returning to life with extraordinary force. Mount Shasta fits this pattern perfectly. Its recent quiet period is insignificant compared with the timescales that govern volcanic systems. Standing approximately 14,179 feet, or 4,322 meters above sea level, Mount Shasta ranks among California's highest peaks. More importantly, it towers nearly 10,000 feet, or over 3,000 meters, above much of the surrounding terrain. This immense vertical relief allows volcanic material, snow, ice, water, and rock to move downhill with tremendous speed whenever gravity gains the slightest advantage. Unlike many isolated volcanic cones, Mount Shasta is actually a complex volcano composed of several overlapping cones built during different eruptive periods. Rather than growing from a single, uninterrupted sequence of eruptions, it evolved through repeated cycles in which older volcanic structures partially collapsed before newer ones emerged. The mountain visible today represents only the latest chapter in an extraordinarily complicated geological history. Geologists studying lava flows surrounding the volcano have reconstructed this history layer by layer. Ancient lava hardened into basalt, andesite, dacite, and other volcanic rocks. Explosive eruptions deposited thick accumulations of pumice and ash between successive lava flows. Each eruption altered the volcano's shape slightly until gradual changes accumulated into an entirely new mountain. Some portions of Mount Shasta are several 100,000 years old, while others formed much more recently. This uneven construction explains why different sides of the volcano display dramatically different landscapes. One slope may consist of resistant lava cliffs, while another contains loose volcanic deposits vulnerable to collapse. Such contrasts influence everything from erosion rates to avalanche behavior. The Cascade Range itself exists because an immense tectonic process continues far beneath western North America. Offshore, the oceanic Juan de Fuca plate slowly descends beneath the North American plate. As the descending slab sinks deeper into Earth's interior, increasing temperatures and pressures release water trapped within the oceanic crust. That water lowers the melting temperature of the overlying mantle, generating magma. The magma does not immediately erupt. Instead, it begins a slow and unpredictable journey upward, through fractures and weaknesses within the crust. Some magma cools underground, forming intrusive rocks. Some stalls for thousands of years within magma reservoirs. Only a portion eventually reaches the surface to produce eruptions. Mount Shasta owes its existence entirely to this continuing tectonic engine. As long as subduction continues beneath the Pacific Northwest, magma generation remains possible. Scientists therefore view every Cascade volcano not as an isolated mountain but as part of a larger volcanic system extending from Northern California into British Columbia. Although Mount Shasta has not produced a major eruption during recorded American history, geological evidence leaves no doubt that it remains active. Its most recent eruptive period occurred only a few centuries ago, likely sometime during the late 15th century. From a geological perspective, that interval is remarkably recent. volcanoes capable of remaining quiet for many thousands of years can easily experience another eruption after only several centuries of apparent inactivity. That understanding explains why researchers continue monitoring seismic activity, ground deformation, volcanic gases, and changes within the surrounding hydrothermal system. Each measurement helps scientists distinguish ordinary background activity from possible signs that magma is moving upward once again. Yet magma alone does not explain why Mount Shasta commands so much attention. One of its greatest hazards comes from something far more familiar: ice. The broad white mantle covering Mount Shasta appears peaceful throughout much of the year. Visitors often admire its glaciers without recognizing that they dramatically increase the volcano's destructive potential. Mount Shasta contains the greatest volume of glacial ice of any volcano in California. Several major glaciers occupy high elevations around the summit, including Whitney Glacier, Hotlam Glacier, Bolam Glacier, Conwakiton Glacier, Wintun Glacier, Watkins Glacier, and Mud Creek Glacier. Collectively, these frozen rivers store enormous quantities of water locked within compacted ice. That frozen reservoir becomes critically important whenever volcanic heat enters the equation. An eruption does not need to be exceptionally large to trigger catastrophe. Even relatively modest explosions or lava interacting with snow and ice can melt vast quantities of frozen water in an astonishingly short period. Unlike ordinary flooding, volcanic meltwater immediately mixes with loose volcanic ash, shattered rock, soil, and older deposits accumulated on the mountain's steep slopes. The resulting mixture transforms into lahars, among the most destructive natural hazards associated with volcanoes. A lahar resembles flowing wet concrete rather than ordinary water. It contains mud, boulders, tree trunks, volcanic blocks, and sediment moving together as one powerful mass. Entire forests can be uprooted. Bridges disappear beneath debris. Roads vanish. Buildings collapse under impacts far exceeding those produced by normal floods. Because lahars follow river valleys, they often travel far beyond the volcano itself. Communities located dozens of miles downstream may face danger despite remaining well outside areas affected directly by lava or falling ash. Mount Shasta has produced numerous lahars throughout its history. Evidence preserved within surrounding valleys reveals deposits tens of feet thick, extending for remarkable distances from the volcano. Some ancient mudflows traveled more than 30 miles or nearly 50 kilometers from their source before finally slowing. Scientists know these events occurred because volcanic debris now lies far from where it originated. Enormous boulders resting within valley sediments once formed part of the volcano itself. Their journey required extraordinary forces that ordinary rivers simply cannot generate. The presence of extensive glaciers means future eruptions possess immediate access to tremendous water supplies. Even if lava never reaches nearby communities, rapid ice melting alone may initiate destructive mudflows. The relationship between volcanoes and glaciers represents one of geology's most fascinating interactions. Ice exerts tremendous weight upon volcanic slopes, influencing erosion and valley formation over thousands of years. As glaciers slowly advance downhill, they scrape away enormous volumes of rock, carving deep U-shaped valleys while transporting sediment toward lower elevations. At the same time, volcanic eruptions repeatedly reshape the glaciers themselves. Ash darkens ice surfaces, reducing reflectivity and increasing solar heating. Lava creates barriers that redirect glacial movement. Explosive eruptions blast away accumulated snow while depositing fresh volcanic material that later becomes buried beneath new ice. Each process continuously modifies the other. On Mount Shasta, glaciers occupy steep channels naturally aligned with future pathways for meltwater. During volcanic unrest, these same channels become efficient conduits capable of directing lahars toward surrounding valleys with alarming efficiency. This combination of steep slopes, abundant volcanic debris, and significant ice accumulation creates a hazard profile unlike many other Cascade volcanoes. Scientists frequently compare Mount Shasta with volcanic disasters elsewhere around the world to understand what similar processes might produce. One of history's most devastating examples occurred when volcanic heat rapidly melted snow and glaciers, unleashing catastrophic lahars that overwhelmed communities far from the eruption itself. Those events demonstrated that water generated from melting ice often causes greater destruction than lava. Lava generally advances slowly enough for evacuation. Mud flows frequently do not. Moving at highway speeds along confined valleys, lahars can provide little warning once they begin. Their enormous density enables them to carry vehicles, houses, bridges, and mature trees together within the advancing flow. Understanding this distinction has become central to modern volcanic hazard planning around Mount Shasta. Researchers have carefully mapped ancient lahar deposits to identify valleys most likely to channel future flows. These maps assist emergency planners in developing evacuation strategies based upon geological evidence rather than speculation. The volcano's structure adds another layer of complexity. Unlike symmetrical volcanic cones often illustrated in textbooks, Mount Shasta possesses an extensive system of overlapping lava domes, flank vents, parasitic cones, and older volcanic remnants. One of its most recognizable features, Shastina, forms a prominent subsidiary cone rising along the western flank. Shastina itself reaches approximately 12,330 feet, or 3,759 meters above sea level, making it taller than many famous mountains despite representing only one component of the larger volcanic complex. Its existence illustrates that magma has repeatedly exploited different pathways through the volcano, rather than always erupting from the central summit. Future eruptions, therefore, may not originate precisely where many people expect. New vents can develop along the volcano's flanks if rising magma encounters fractures, providing easier routes toward the surface. That possibility broadens the range of areas requiring careful monitoring. Scientists continuously study earthquake activity surrounding Mount Shasta because earthquakes often accompany magma movement underground. Small seismic swarms sometimes occur naturally as rocks adjust to regional tectonic stresses. Distinguishing ordinary earthquakes from volcanic unrest requires detailed analysis involving earthquake depth, frequency, location, and wave characteristics. Most detected earthquakes around Mount Shasta remain small. That observation provides reassurance, but not certainty. Volcanic systems commonly produce long intervals of quiet interrupted by relatively rapid changes. Continuous monitoring therefore remains essential regardless of how peaceful the mountain appears. Modern monitoring extends far beyond seismometers. Sensitive satellite radar measures ground deformation with astonishing precision. Even subtle swelling only fractions of an inch or millimeters across broad regions may indicate magma accumulating underground. Global positioning system stations continuously record tiny changes in elevation and horizontal movement. Gas monitoring provides another critical window into the volcano's interior. Magma releases carbon dioxide, sulfur dioxide, water vapor, and numerous other gases. Increasing gas emissions sometimes precede eruptions by indicating fresh magma approaching shallower levels. Scientists also examine hot springs, fumaroles, and hydrothermal areas where volcanic heat influences groundwater circulation. Changes in temperature or chemistry occasionally reveal evolving conditions beneath the surface. Mount Shasta possesses active hydrothermal systems despite its long eruptive pause. Warm groundwater circulates through fractures deep within volcanic rocks before emerging at springs around the mountain. These systems demonstrate that substantial heat continues existing underground. Hydrothermal circulation contributes to another lesser-known hazard. Hot, chemically active water gradually weakens volcanic rock through alteration. Strong minerals transform into softer clay-rich materials that possess far less structural strength. Over thousands of years, this invisible chemical weathering weakens portions of the volcano from within. Eventually, gravity may exploit those weakened zones. Geological records reveal that Mount Shasta has experienced enormous sector collapses during its history. One particularly massive collapse removed a significant portion of an earlier volcanic edifice, sending an immense avalanche of rock and volcanic debris racing across surrounding terrain. Deposits from that event extend astonishing distances beyond the mountain. Such collapses need not coincide directly with major eruptions. Sometimes gravitational instability alone proves sufficient. Other times, earthquakes or rising magma provide the final trigger. These possibilities reinforce why scientists evaluate Mount Shasta as an evolving geological structure rather than simply an eruptive volcano. Every glacier, lava flow, hydrothermal system, fracture, and valley contributes to the mountain's overall behavior. Climate also influences volcanic hazards in subtle ways. Seasonal snow accumulation determines how much frozen water becomes available for rapid melting during eruptive activity. Heavy winters increase potential lahar volumes by storing larger quantities of snow and ice across upper elevations. Long-term glacial retreat introduces additional complications. As glaciers shrink, they expose fresh volcanic rock previously protected beneath ice. Newly uncovered slopes often experience accelerated erosion, increasing loose sediment available for future debris flows. Changing glacier geometry also alters drainage pathways. Scientists therefore study glaciers not merely as indicators of climate, but as dynamic components of volcanic hazard systems. Visitors climbing Mount Shasta frequently notice deep gullies carved into its slopes. Many originated through repeated debris flows generated by intense rainfall, rapid snowmelt, or smaller volcanic events. These channels effectively record thousands of years of interactions among ice, water, gravity, and volcanic deposits. Future lahars would likely exploit many of the same routes. Fortunately, modern hazard planning recognizes these patterns. Emergency managers coordinate closely with geological agencies to maintain awareness of evolving conditions. Monitoring networks provide continuous streams of information, allowing rapid detection of unusual activity. Preparedness remains the greatest defense because eruptions rarely occur without at least some detectable warning. Warning, however, does not necessarily mean certainty. Volcanoes remain among Earth's most complex natural systems. Magma movement varies enormously between different volcanoes, and even between successive eruptions of the same volcano. Some eruptions develop gradually over months. Others accelerate within days after prolonged quiet. Researchers therefore avoid making simplistic predictions. Instead, they continuously evaluate probabilities based upon every available observation. That cautious scientific approach explains why Mount Shasta continues receiving careful attention despite its peaceful appearance. Its geological record repeatedly demonstrates that quiet periods eventually end. Ancient lava flows visible today once emerged as molten rivers descending fiery slopes. Ash layers now hidden beneath forests once darkened skies across distant regions. Valleys occupied by modern highways once carried torrents of volcanic mud generated by rapidly melting ice. The mountain has transformed repeatedly throughout its lifetime, leaving unmistakable evidence preserved within surrounding landscapes. For nearby communities, understanding that history provides practical value rather than merely satisfying scientific curiosity. Every mapped lahar deposit helps define safer development areas. Every seismic station improves detection capability. Every satellite measurement refines understanding of underground processes. Every glacier survey strengthens estimates of future hazards. Together, these efforts reduce uncertainty while acknowledging that uncertainty can never disappear completely. Mount Shasta commands respect precisely because its greatest dangers arise from interactions rather than isolated events. Magma alone presents hazards. Ice alone presents hazards. Steep slopes alone present hazards. When combined, those elements amplify one another. Heat transforms ice into torrents of water. Water mixes with volcanic debris. Gravity accelerates the resulting mass downhill. River valleys focus destructive energy toward populated areas. Each step builds upon the previous one until an eruption becomes far more than an explosion at the summit. That interconnected system explains why scientists often emphasize the volcano's glaciers whenever discussing future risk. The frozen cap crowning Mount Shasta is not simply an attractive alpine feature. It is an enormous reserve of potential floodwater resting directly atop an active volcanic system. Its existence fundamentally changes hazard assessments compared with volcanoes lacking extensive ice. The mountain's strange history ultimately reflects continual transformation driven by fire and frozen water working together across immense spans of time. Massive eruptions built towering cones only for collapse to erase them. glaciers carved valleys that later guided destructive mudflows. Hydrothermal fluids quietly weakened rock while tectonic forces continued generating fresh magma far below. Each process unfolded at its own pace, yet all became connected within one remarkable volcanic system. That is why Mount Shasta remains under constant scientific observation. It is not fear that keeps researchers returning to its slopes year after year. It is evidence. Every layer of lava, every buried ash deposit, every ancient lahar, every glacier clinging to the summit, and every subtle tremor recorded beneath the mountain points toward the same conclusion. Mount Shasta has never been a static monument. It has always been changing, and although those changes often occur too slowly for a single lifetime to witness, geology leaves little doubt that the mountain's next chapter will eventually arrive. Until then, the snow-covered giant will continue standing quietly above Northern California, appearing serene while preserving within its icy crown and volcanic heart all the ingredients that have shaped one of the most fascinating and closely watched volcanoes in North America.